as I told you this morning, unfortunately we had 2 cancellations this week. So we discussed with the other organizers, and we thought that instead of adding some new material, we thought it would be better to just try to give some kind of long tutorial to maybe come back on some aspects that have already been discussed and try to make bridges between the different lectures. So that's what this is my goal. I set up a list of detailed goals that is quite ambitious, so then we will see. The game will be to check how many I failed to achieve. But anyway, the idea is basically to introduce what I think is basically the simplest SAT-and-SAT transition. In this way, I hope to make a bridge with the lecture of Chris Moore that discussed in general the problem of SAT-and-SAT transitions. The simplest SAT-and-SAT transition will be computed by one of the simplest replica calculations you can do. So this should make connections with replicas, so with the lectures of Giulio and Florent. Then I will illustrate replica symmetry breaking very briefly, and Federico will start tomorrow to discuss replica symmetry breaking in a more complete way. But I will discuss the fully connected case, and Federico will discuss models on tree-like graphs, so diluted models. There will be a difference, but I hope you will see the connection. And then I would like to connect this SAT-and-SAT transition to jamming, to convince you that it's basically the same thing. And this should, unfortunately, Andrea Liu could not come. She was supposed to introduce the jamming transition, but this will be done later this week by Sid Nagel and Karen Daniels. And then I hope I will also discuss a little bit the relation between spin and particle glasses that has been already discussed by Giulio and Gilles, and there will be a specific connection with the lectures of Ludovic Berthier. And finally, I hope to give you some physicist perspective on the problem of packings in large dimension that has been discussed from the point of view of a mathematician by Enrico. Okay? I'm not sure I will be able to do all this, but anyway. So this is the outline for the first lecture. I don't have lecture notes, unfortunately, because I didn't have much time to prepare it, but I have some handwritten notes that I can scan and give you. But anyway, most of what I'm going to say today is based on this paper, which is published on SciPost. If you don't know what is SciPost, please check it. It's a very nice journal. It's a really open access journal. It means that you don't pay and the readers don't pay. It's basically archive plus a reviewing process, okay? And it's handled by physicists, by scientists for scientists. And it's a nice initiative, so please check it. Anyway, so you can read it for free. You don't have to pay. It's also an archive, but anyway. Now let's start. So I will define the perceptron, which has been already defined by Florent, and I will use exactly the same notation. Okay, so so this will be, I put the outline there so I can try to follow it. So this will be 1A, definition of the perceptron. So you can think to the perceptron as the simplest model of a neuron. So you have some input. Let's call the input phi 1, phi 2, up to phi n. Okay? So you have n channels that are sending an input, and then you have an output. Let's call it y. So the input will be some vector phi. So it will be an n-dimensional vector. And the output is going to be just the sign of some vector x times phi. And I hope this is exactly the same notation that Florent used. So, which means that on each link there is a weight, x1, x2, up to xn. And what the neuron, this model neuron, is doing is that it's taking a linear combination of the input according to these weights. So this is the scalar product of x and phi, and then you take the sign. So if it's bigger than 0, you return 1. If it's smaller than 0, you return -1. You can think, you can use 0, 1 instead, but it's basically the same. Okay, so this was introduced by, as Florent said, by Rosenblatt in, I think, 1957. And, now, once you have this, you can ask many questions, which are different. Okay, so what Florent discussed is the is like a more inference or machine learning perspective. So the idea of Florent is that there was a teacher that prepared in some way a vector x, okay? So the teacher knows the vector x, okay? And it's using this vector x to prepare many, so it prepares many inputs, and for each one it gives you the corresponding output, okay? So you have a list of inputs and outputs that are produced, and you have a lot of them, I mean, that are produced with some weights that you don't know. And what you have to do, so you are the student, you get these input outputs, you know all of them, and you have to reconstruct x star or some good approximation of x star, so that you are able to understand the relation between the input and the output, okay, more or less. Now, this is not what I'm going to do. I'm going to take a very different perspective, sorry, Florent, which is I give you some input-output relations. So same thing, phi1, y1, and so on. But these are not prepared by some other perceptron. There is no relation like this between the phi and the y, okay? And the quest, so I have a certain number of them. I have m of them, okay? And the question is, can I find some vector x such that y is equal to sine of x dot phi for all of them? Okay? But the point is that I have no guarantee that this x exists. In the teacher-student setting, I know that the y are prepared from the input using the perceptron, so I know that there is a solution. Here I don't know. Maybe there is no solution. If I have too many of them, there is no solution in general. Okay? So this will be more a constraint satisfaction perspective, because what I want to do is that I want to find x that satisfies these constraints for all mu. Okay? Yes?
So does it mean, like, could you separate the minus ones and ones by a hypothesis?
Yes, yes. So it's also a classifier if you want. Now the point is that I'm going to add one more simplification that was already discussed by Chris, which is that I will take the inputs and outputs completely at random. Okay, so what I'm going to do, so let me erase this because it's not what I'm going to do. So what I'm going to do is that I will take each component of the input as a random Gaussian variable with 0 mean and variance 1 over n. Okay, this notation has already been used several times, but it's just a Gaussian with 0 mean and variance 1 over n. And I will take y mu as plus minus 1 with probability 1/2. So this means that the input-output relation is completely random, so it's not even really a classification problem, right? Because even if I'm able to classify all of them, you give me one more, it's totally random. I cannot predict in any way how it's going to be classified. So it's not a classifier, it's really a random constraint satisfaction problem. So this is really, so I will write it here, it's going to be a random constraint satisfaction problem. It's really like the problem of random k-sat that Chris discussed. You have a bunch of constraints on some variable. Here, x are the variables. The constraints are totally random, and you want to know if there is a solution to this set of constraints. Okay. Now, okay, this was already part of 1b. So I'm already messing up with the outline, but anyway. Now, there are two things that I have to add. So first of all, you see that having this relation is exactly equivalent to imposing that y mu times x dot phi mu is positive. Okay, it's the same thing. Okay, these two things should have the same sign, so the product should be positive. So then this means that basically y mu is irrelevant because I'm taking the phi at random. They have plus minus. They have zero mean. They are Gaussian. So the probability of having phi or minus phi is the same. So the fact that I'm multiplying by a random plus minus 1 is not important. Yes?
Making everything fully random is equivalent to the thinking of the RAM. We don't really know what's going on.
I mean, the RAM is a random model where the energies are random, but there are no constraints to satisfy.
True, but there was obviously a process that we thought of before we made them fully random, right? So there is no thinking.
Yes, okay, yes. There is no part. No, it's just, I mean, if you want, Chris and Guillaume gave you some motivation to use random ensemble of constraints. Guillaume motivated it by error correction. So if you want to do error correction, it's a good idea to take random ensemble. And Chris also gave other motivations that I don't remember. But anyway, I mean, there are good motivations. And you can always use this as a benchmark to understand this first and then, OK. So I was saying, OK, so basically, this means I can drop this y. OK? I will just drop it. So these are my constraints. And actually, the second thing I will do is that I will generalize it a little bit by adding here, instead of this 0, I will put some sigma, where sigma will be a positive number for the moment. So there is a good motivation for this. I mean, this is discussed in the paper by Derrida and Garner in 1988. So the requirement to have sigma positive instead of 0 is because of some stability issues. So, but it's not very important. I mean, for the moment, just take it as a constraint. If you don't like sigma positive, just suppose sigma is equal to 0 will be a particular case of what I'm going to do. OK?
Again, why you cross y?
Why remove y? Because phi is a random Gaussian variable with 0 mean. So the probability of having a vector phi or the opposite one is exactly the same. So the fact that I'm multiplying on top of that by a random sign is not going to change anything. If you want, I'm redefining phi times y equal to phi, and it has the same statistics. OK, the last thing I need to do to complete the definition is that think geometrically to what you are trying to do. So think in this way. OK, now these are going to be our constraints. The constraints I want to satisfy. So if you think geometrically, what you have some vector phi 1. OK? And now then you have your vector x. And what you are trying to satisfy is that the scalar product of these two vectors should be positive. OK? So the vector x should belong to some cone around the vector phi. Okay? So this region is forbidden by the constraint, and this region is allowed by the constraints. Now, there are two things, however, that first thing is that in the original problem, if I multiply x by some arbitrary number, this is still a solution because I'm taking the sign. Okay? So this means that if x is a solution, also lambda x is going to be a solution. So, and this means that basically the space of the possible solutions is always infinite. Okay? So since I'm going to try to compute the volume of the space of the number of solutions, I will just fix a normalization for x. So I will decide that x is going to belong to a sphere. So I will add the constraint that the sum over I of xi squared should be equal to n. Okay? I will just normalize them. In any case, if one is a solution, all the other are solutions. So I just fix one, and I take this one. Okay? So, and this is the spherical constraint that you have already seen in the P-spin model. Okay? So this is going to be a spherical, instead of P-spin, perceptron. Okay, so maybe let's just now summarize. So my goal is to find a vector x such that x square is equal to n, and x times phi mu is bigger or equal than sigma, or if you want, let's write it in this way. X dot phi mu minus sigma should be positive. I will call this h mu of x. Okay, and this should be true for all mu equal from 1 to m, and that's it. Okay, so this is my problem. Okay, where the phi are taken from this. I will copy it here so then I can erase the other blackboard. These are just random Gaussian variables. Okay, so now I want to rewrite this as a StatMech problem, like Chris did for the KSAT. Ah, sorry. I have changed my notation. So I'll call this big R, not H. So R mu. Okay. So what can I do? So this is, you can do it anytime you have to satisfy some constraints. You can encode the constraints in Hamiltonian. So I will write my Hamiltonian, which is a function of x, as the sum from mu equal to 1 to m of some potential v, which will be a function of R mu of x. So it will be also the same potential function of x dot phi mu minus sigma. Now v is arbitrary, but what I want to have that h is equal to 0 if all the constraints are satisfied. So what I'm going to choose is whatever potential v, which should be some function of some argument h. Now I call h the argument of v. And it should be something like that. So it should be, what I want to have is that v is positive when h is negative, and v is 0 when h is positive. Okay? What? Now, R is this function, and h is the argument of v. If you want, I call it x, but for the moment, it's arbitrary. Then, of course, it will be soft spheres, and I'm going to discuss jamming. But for the moment, it can be any potential. The important point is that if I choose a potential like this, if all the constraints are satisfied, then this means that all these arguments are positive. The sum is then all the potentials are 0, and my Hamiltonian is 0. If there is at least one constraint that is not satisfied, then this has a negative R, and then the energy is going to be positive. Okay, this.
I missed why the constraint is you want x dot phi to be bigger than sigma. You would think you want it to be as close to 0 as close to 1, plus minus 1.
No, in the original problem, sigma was 0. In the original Perceptron problem, I just want to know if x dot phi is positive or negative. So I put 0, sigma equal to 0. But then I just say that I will generalize it to any positive sigma, just for fun. There is no. If you want, just think that sigma is 0. It will not.
Yeah, I guess what I'm missing is I would like fundamentally what I would like is x's that satisfy the y equals to sine of x dot phi equation.
Yes, which is equivalent. Sorry, I did it here, but. This is equivalent to say that y times x dot phi is positive. Okay? Then I drop the y because I said, okay, y is just a random sign that I am adding to an already random vector. Okay? Is it fine?
Well, but really you try to solve it for a particular set of phi's, right?
Yes. So if you want, I can change the name, but if you want, I can call y times phi. I can call it phi prime. And the point is that then I'm going to take random phi, and then if it's random Gaussian, the fact that I'm multiplying by plus minus 1 is not important. Okay? Or if you want, you can fix that. You can think that the y I choose the y to be all 1, which is another possible choice. Okay? In any case, so if you prefer, let's say, okay, the y are all 1, and the phi I take them random. Okay? Okay. Then I write this Hamiltonian, and then what can I do? So okay, with this I have that h of x is equal to 0 if and only if x is a solution, and h is positive if and only if x is not a solution. And now the question is that I want to answer is, are there solutions? So what can I do as a statistical physicist? It's already discussed. I can try to count the solutions. So what I'm going to do, I will introduce a partition function, which should be the integral over dx of the product over mu. If you want, let's write it first as exponential of minus beta h of x, where here dx will be the dx1 dxn times the delta function of the spherical constraint. Okay? So this is the integration over x on the sphere. Okay? It's the uniform measure over the sphere. And okay, then I have this factor, which means when I send beta to infinity, I have two possible. I mean, if there are solutions, then this will be concentrated on the solutions that have 0 energy, that have the lowest possible energy, and so this factor will become 1 on the solutions and 0 on all the other states. So this will be just the volume of the solutions. Okay? If there are solutions. If there are no solutions, when beta goes to infinity, this is going to go on the lowest energy state, and so I will have a positive energy. So I want to study this thing in the 0 temperature limit. Fine?
Does it make sense for non-zero temperatures?
Sorry?
Does it make any sense in non-zero temperatures?
Not for this problem. I mean, unless you want to allow for some. If you take finite temperature, it means that you can allow me to violate some constraints with some probability. Okay, and then I will just rewrite this in a different way because I'm going to use it next. I'm going to write this as integral over dx of, so this thing is the product over mu from 1 to m of exponential of minus beta v of r mu minus sigma, and then I will put here a delta function of r mu minus r mu of x, and I will also integrate this, over, okay, I hope you can read, but this is an integral over r mu. Okay, so I did nothing. If you integrate over r mu, sorry, it's r mu. Okay, let's rewrite it complete. This will be the integral over dr mu. Is it better? No.
Yes, yes.
Okay. So if you see, if you integrate over this small r, you have a delta function, so small r is equal to big R of x. So you replace it here, and then you have just the product of the exponential of minus beta v, which is the original Hamiltonian. Poor me, I made a mess. Okay, you're right. No, I'm sorry. This is just that I made a mess. Sorry, let me correct because I'm changing notations all the time. And I want to be so. I'm going to call R just x dot phi, and this should be bigger than sigma. Okay. I'm sorry. So please correct. And then here I should have a minus sigma. Is it fine? Sorry for the confusion. So R is this. And so if you want, I can put it here explicitly. I will put here x dot phi mu. OK? OK. And now I just need one more step. So you remember this integration measure is just dx times the delta. And this, now I will do just one additional step, which will be to write this as integral over dx. I'm going to introduce one more variable, k mu. Then I have exponential of minus beta v r mu. OK, my r is not always the same. And then this delta, I will write it as plus I k mu times r mu minus x dot phi mu. And here I will replace this by proportionality. This is there. So the only thing I've done, I use the integral representation of the delta function as integral over k of e to the I xk. Okay? And I get this. OK. I mean, I'm dropping some 2 pi's here, but I don't care too much about proportionality, because the proportionality constant will just multiply the space of the solution by a constant. But I want to know if the space of solution is 0 or not, so I don't care if it's multiplied by constant. If you want, I'm shifting the entropy by constant. I don't care. OK. Now we are ready to do replicas. OK, and then final thing is that I'm going to define my free energy. Let's write it here as minus t log z. OK, this is not very new for you. OK. So now let's see. This is OK. Back the outline. So this is the end of point C. I'm sorry, this was 1C. And now let's move to replicas. So you see, the problem is, I mean, as usual, the problem is that this thing depends on the disorder. The disorder here are the phi. And of course, I don't know how to compute it for general phi. So what I'm going to do is that I'm going to hope that this thing is self-averaging. Actually, it is. And then I will take an average. For a random phi? You mean on a given, OK, on finite n, yes, I know. But then I don't know how to take the thermodynamic limit. OK, because of course for any n, I'm going to change the phi. And OK, so I want to take the average over the phi. This over bar is going to be the average over the phi.
We are only interested in the differential function. Why do we all take the log?
OK. Of course, the log and the free energy. I mean, if I know f, I know z and the inverse. But the problem is that when I take the average, I need to take the average of the log, because the log is the quantity that is self-averaging. So when I mean, the log will, for n going to infinity, the log of z will, with probability 1, be equal to some value with fluctuations that are small. If you take z and you average z, this is not going to be self-averaging. But this has already been discussed, so I don't come back to that. OK, so now we want to take this. And as Giulio said, OK, for this we can use the replica method. So I'm going to write it in. OK, everybody has his own way to write it. I like this one, but it's the same. I mean, you take the derivative and you get the log. And I also can write it actually as minus t times the derivative of log z to the n. It is the same because when I take the derivative, I get 1 over z to the n times the derivative of z to the n. But for n going to 0, z to the n is 1, so okay. Anyway, this is really not. I mean, you can take the one you like. In all cases, what you have to compute now is this object, z to the n. So if I compute now z to the n, so you know when you, I mean, if z is an integral over some stuff, so if you have an integral, if you have integral of some function f, and you write it to power n, you can write it in also as integral over x1 f of x1, x2 f of x2, blah 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 up to n. Okay. So so this thing is going to be the product over a from 1 to n. Okay. You know, I'm doing the replica method, so I'm going to choose integer n and then do the analytic continuation and so on. This has already been discussed. So then I just need to copy that integral there. So I will have some xa, then I have this r mu with an index a, and I have k mu with an index a. Here I have a product over mu, and then I have e to the minus beta v of r a mu minus sigma plus I k a mu times r a mu minus I k a mu x a phi, sorry, x a phi mu. Okay. So, and now I have to take the average of this thing. No, because the phi are the same for all the replicas. Okay, otherwise I'm doing nothing. So what I want to do is really to, so let me isolate this term, which is, now you see this term is the only one that depends on phi. So you see now why I was doing this Fourier transforms. And now I want to take the average over phi. Okay? And now the phi are Gaussian. So this is the average of exponential of phi over a Gaussian, so you know how to do it. I will write it here, the result. So what you get is exponential of I times this. Okay, here I have this term, I have a product over mu, and I have a product over a. So I'm going to bring it in the exponential. It's going to be exponential of minus I times the sum over a and mu of k a mu x times phi mu that I want to average. Sorry, xa, thank you. And this is going to be exponential of minus 1/2 sum over a and b and mu of ka mu kb mu times qab, where qab is 1 over n xa dot xb. So, you know, if you don't remember, so this is a Gaussian integral, right, with a linear term. Just one trick, I don't know if you, perhaps you all know it, but one trick I use always to do this integral, you just develop this in a Taylor expansion. So you write this as 1 minus I times this. You take the average is 0. You take the second order term. The average gives you this. Then you have all the other terms, but you know that for Gaussians, you don't care. The other terms are trivial functions of the second cumulant, so you bring it back in the exponential and you get the result. Okay, so you use this and put it here. So now what I get is z to the n is going to be integral over xa R A mu and K A mu. Then I have exponential of minus beta sum over A mu V of R A mu minus sigma. This is the potential term. Then I have this plus I sum over A mu K A mu R A mu. And then I have this last term, which is minus 1/2 sum over AB and mu of K A mu KB mu QAB, where QAB is a function of x defined by this. Okay. Oops. Okay.
Have you dropped the product over the A's?
I'm sorry, no. I mean, I put the sum over A here, and so this is a, would you mind if I write, this is implicitly a product over all the differentials of all the things, okay? Otherwise I have to put, so these things are it's the product over A and mu of all the differentials, okay? And now you see what happens is that now the integral over mu, I have m copies of the same integral, right? Because here everything appears as a sum over mu here. So what I can do, perhaps I'm going to do it here just to avoid copying everything. This is just going to be the integral over just one index mu. To the power m, because I have m constraints. And I have one integral for each of them. But they are all identical once I take the average over phi. So this is, perhaps you have already seen this when Chris did the first and second moment calculations, when he computed the average of z, not the z to the n, but he said, okay, I have many constraints, and each constraint is independent and will act in the same way. So I just take the average of one constraint and I multiply by, okay, so it's exactly the same thing, okay? Once I take the average over the disorder, all the constraints give me the same contribution, and I just get this to the power m. Little n. Where? No, the n is the index a. A goes from 1 to n, and I have n variables x. Other questions? Okay. So now you see. Now what do I get? What I can write this as the integral over this xa of some function I of q to power m. Okay, q is a matrix. Is a n. Q is a small n by small n matrix. I, which is all this thing in the parentheses, is some function of q. And I have I to the power m, and I have to integrate over this x. Now, this is easy, because now what you see is that if you want to have these vectors, you have the sphere. So this is the sphere of radius n. So you have the n replicas, x1, x2, up to x little n. Okay? And you have to integrate over all of them, but you have to integrate a function that depends only on the matrix of the scalar products. So this function is rotational invariant. If you take a global rotation of all the replicas, it's the same. Okay? So you know, if you integrate, if you are in d dimensions and you do the integral over x of a function that is rotational invariant, this is easy, because this is just the solid angle times the integral over x to the d minus 1 f of x, right? Now so this is the integral of a rotational invariant function of only one vector. Now I have a rotational invariant function of little n vectors, so I have to generalize this. But I have a formula that is easy to derive, and I can give you a reference, or so if you have the integral of a function f of the x a, so you have little n vectors, okay, and this function is rotational invariant, then you can write this as the integral over a matrix Q, I mean some constant that depends on, so these are n-dimensional integrals, okay? You have some constant that depends on large n and little n, and then you have the integral over Q. So Q is the matrix of all the scalar products, and then you have a Jacobian. The Jacobian is just the exponential of n minus 1 over 2 times the log of the determinant of Q, and then here you have f of Q. Okay? So this is really easy to show. But so basically, so if the function f is rotational invariant, it can only depend on the scalar products. So and then you have this thing. So I'm going to put it there. Little q is by definition here is the xa dot xb. Let's divide it by. Sorry, it's small q. It's little q.
No, but so it's the exponential of
Here?
yeah.
It's sorry. Okay, it's n minus 1 over 2 times the logarithm of the determinant of q. This is just the Jacobian of if you want, this is the volume of the space of all the rotations of a given set of vectors. It's exactly the same as this x to the d minus 1. Okay? Okay. So I put it there, and what I get is that my z to the n. So you see then what? Okay, two things. Here I have the differential that contains the spherical constraint, but the spherical constraint is also rotational invariant. It's just a constraint on the length of the vectors. So I will put it into the function f, and then I have I of q. So let me write the result, and then we can see if we agree. So I drop all the proportionality constants as before. So I write this as the integral over little q of the exponential of n over 2 log that q. I will drop this because I want to take the thermodynamic limit. Okay, so large n, which is the number of particles of variables, is much bigger than little n, that is the number of replicas. If you did Julius exercise, you should be convinced. Otherwise, we can maybe. Okay, then I get this term. Then I get the product over a of some delta function of q a minus 1. So this is the spherical constraint, okay? Because q a, what I'm saying is that little q here is large q, okay? Large q, I'm using two different notations because large q is a function of x, while now little q is a dummy variable, it's just an integration variable. So, yes, sure, sorry. The problem is that I didn't want to erase the other one. Okay. So I'm here, okay? So the integral over x is replaced by the integral over q. I get this Jacobian. I get the spherical constraint that tells me that QAA should be 1. And then I just get I, where I replace large q by little q to the power m. And I, now I can write I. Where?
When you say dq hat, there are many.
Sorry. Yes, you're right. dq hat in this formula is the product over a smaller and equal than b of dqab. Because q is symmetric, is the matrix of the scalar product. So qab and qba are the same. And so I have to integrate only with over a smaller or equal than b.
be iterating independently over every QAB, right? Because the Q has to be at that form that it does.
Okay, so the Q satisfies some like triangular inequalities. So the point is that the space of this I didn't specify the space of this integration.
Yeah.
True.
Just overall valid Q.
So I have some constraints that QAB should be smaller than square root of QAA, QBB, and stuff like that. Yes, that's true. But the log that Q is taking care of that. You can see that when the matrix Q is not good, the log that of Q is going to become singular. And I mean, if you want that Q is going to go to 0, and I can give you a reference to prove this formula if you don't. But it's just a generalization of spherical coordinates. Okay. You can do it for 2 vectors, and it's easy. And okay, so I was here, and now the function I of Q was defined inside this parenthesis. So you see that just to simplify it a little bit, so I can write it here. You see that the integration over K now is Gaussian again, okay? Because K is quadratic here and is linear here. So I can write I of Q. I will not need it, but just for completeness, I mean, I will need it, but I will not use it explicitly. So I can write it as integral over RA of exponential of -1/2 sum over AB of Q minus 1 AB times RA RB divided by square root of 2 pi to the n times the determinant of Q. Sorry, little q. Times the exponential of minus sum, okay, of the potentials, okay, V of RA minus sigma. So what I only did is that I did here I did this integration over K, and you see that this is KA, KB as correlation QAB. When I integrate and I'm doing an inverse Fourier transform, I just get that RA, RB as correlation Q minus 1 AB. Fine? Okay. So I am done. So you see that now this thing is only a function of QAB. And QAB, so I don't have any more large n variables in the integral. I only have little n square variables that are QAB. Okay? So I get that z to the n is in integral over Q of exponential of n times some function a of Q. Letizia called it S, but I'm calling it A because I will need S for another thing later. And A, so here now you see I can use this delta function to integrate over the diagonal elements. So the diagonal elements are 1. So here this is just, if you want, is the product over A smaller than B. I don't have anymore the integration over A equal B because QAA is just 1. And A of Q is going to be 1/2 log that Q plus alpha, because I perhaps forgot to say that as usual I will take the limit n and m going to infinity with fixed ratio m over n, and here I get alpha times the logarithm of I of Q. Okay? If you're lost, now I can come back and re-explain things. If I will give you a few minutes to think, a few seconds to think if you're lost. How many people are lost? So tell me where.
I just want to make sure I'm understanding the structure of this product correctly, the product from A less than B. So we're taking ZBN, which is a scalar, and we have this integral expression. And then are we, when you're doing this product of all of the A, are you fixing B, or are you have like an outer product outside that?
Sorry, no, I have a matrix QAB.
Right.
So this is going to be n times n. Now, so I started with a problem with n vectors on the sphere, right? When I did the average over the disorder, I realized that actually my function there was only a function of the scalar products. So I said, OK, then I can just say, OK, instead of integrating over the vectors, I just integrate over all the possible scalar products. For a given configuration of the scalar products, I have the vectors, and I can just rotate them, which gives me this depth of Q. OK? So now the only thing I have to do, I have this matrix Q of the scalar products. The elements on the diagonal are fixed to 1 because of the spherical constraint that I had in the beginning. OK? And what remains free are the off-diagonal elements, with the only thing that the matrix has to be symmetric. So I only integrate over the product of elements that have A smaller than B. So the elements here, if you want, in the upper triangle. And then for each, and then I have this function A of Q that contains 2 terms. This is, if you want, is an entropic term. It counts how many rotations you can make. And this is some term that depends on the constraint. So you see it depends on alpha. And that is taking into account the constraints. OK. Who else is lost? Yes, it's the same. I'm using this notation just to avoid confusion. It's like here. I say that the large R is a function of X. Then I use a delta function, and I say, OK, little r is. You see? I'm saying that I introduce a little r, and then I put a delta function that little r is equal to large R. And there I did the same. Large Q is the function of X. When I introduce.
The 2 little r's are the same. You have the script r and non-script.
Sorry, no, yes, the 2 little r are the same. It's just my writing, sorry. What matters is the large variables are functions of the degrees of freedom of the problem, X, and the little ones are auxiliary the integration variables that I introduced just to do the calculation. So here, little q, I mean, large q was a function of X. It's like, if you want, when you do this, here you have the absolute value of X, and then you introduce an integration variable X. Let's call it R, where R is the. So here, large Q is, if you want, is the absolute value of X, and small q is the integration variable that corresponds to that. It's always a bit tricky, because if you use the same notation, people are confused, and if you use different notations, people are also confused. Yes?
What happened to the K? What happened to the K?
To the K, I just integrated them out because I erased it, but when you write I of Q, you realize that the K are Gaussian in the end. You can integrate them out explicitly. I add it on the blackboard, but it's a Gaussian integration over the K, and they disappear.
Do we still have the constraint over QA on diagonals?
I integrated it explicitly. So I say, OK, here I integrate only over A strictly smaller than B. So I fix the diagonal to 1. And then I leave the other as integration variables. OK? OK, now you see. Now what you see is that, OK, you have an integral over Q of exponential of n A of Q. Q, if you fix the number of replicas, is just as a fixed number of variables, OK, n square variables, little n square. and large n is going to infinity. So you can use the saddle point method, and you can say, okay, the log of z to the n is going to be the maximum over the matrix Q of A of Q. 1 over n, sorry. In the limit when n goes to infinity. Okay? This is clear, because I mean, when n becomes very large, this thing becomes very peaked around its maximum. Okay? Okay, so we are almost done, because you see, I have my formula here. So if I want to know the average free energy, what I have to do, now I got an expression for log of z to the n, which is this. So in principle, the recipe is the following. You fix the number of replicas, and you find the maximum over all the possible matrices Q with the diagonal fixed to 1 and symmetric of A of Q, which is this object, which you can compute is just log that Q plus alpha times this logarithm of this integral. Okay, this gives you the logarithm of z to the n, and then you have to continue the result to real n, I mean real positive, and then you have to take a derivative with respect to n and limit n to 0. Okay, derivative with respect to n and limit of n to 0. At this point, I just want to make a little remark. I mean, many people said, okay, replica method is black magic, is blah, blah, blah. I agree, in part. But I think it's really a calculational tool. So if you think of it as a calculational tool, okay, you have to do this analytic continuation. But once you learn how to do it, it's really like when you do like the epsilon expansion. Okay, when you do the epsilon expansion, you are in the theory of critical phenomena. You say, okay, I start from dimension 4, and now I take dimension 3.98. Okay, you're doing analytic continuation from integer dimension to non-integer dimension. But you know how to do it, and you're not particularly shocked, at least today. So I think it's really the same situation. What you are saying is that, okay, if things go well, you can reconstruct from all the integer moments of a distribution, you can reconstruct the log. Okay. Just yes, the replica interfere because you see that they are now when I did the average over the disorder, because all the replica have the same disorder, I get the coupling between the replicas. I get this term I of Q that is coupling the replicas. Federico, I will come back to that, but for the moment not. Just really take it as a calculational tool. Sorry, this alpha? Alpha is m over n, sorry. Yes, I'm using confusing symbols, but...
Okay, out of m, you factored out n.
Yes, because I have I to the m, so m is equal to alpha n. Then I'm putting it into the exponential, and I get exponential of n times alpha log I.
This only works if this large n limit works when
Alpha is finite. But you will see, I mean, this is the right scaling. Yes, it's the right scaling. You will see that at the sat-ansat transition, alpha is finite. So that's the right scaling you are interested in. Okay? You could scale m and n differently, but then you would just trivially go either into the sat phase or into the unsat phase. Okay, so this is the point 2a of the outline. So this is the general replica method calculation. So this is my final result. Okay. And now the problem is, of course, that in general you don't know. I mean, you don't know how to solve this thing that I wrote, because you don't know how to how to solve this. You have to find the maximum of A for each n, then you have to do the continuation and so on. So what you want to do next is to find some simple way to do this analytic continuation to n to 0, okay? And this is to B. So the first thing you can do is that you can say, okay, but my problem is as a symmetry. The symmetry is that I can, when my z to the n is just a product of n times the same thing. So I can exchange as I want the labels of the replicas, okay? If I say, okay, I have replica 1, 2, 3, but if I change 2 and 3, it's still the same integral, okay? And you can check that the function a of q is also symmetric because it's the logarithm of the determinant of q. And you know if the determinant, if you switch lines and columns, is symmetric. It doesn't change. And the function I of q that I erased is, you can check if you wrote it down, it is also symmetric in the labels. It must be so because at the beginning the replicas don't have any particular labeling. It's arbitrary. So this means that I have what is called a replica symmetry. And now you have to find the maximum of a function that has a symmetry. And in the Ising model you have a symmetry up-down. So your function, you have f of m, which is symmetric under change of sign of m. And you can hope that the maximum also is symmetric. It's not necessarily true. In the Ising model, you know that at low temperature you can break the symmetry spontaneously. But what you can do to start, the simplest thing is, okay, let's try to see what happens if I assume that the replica symmetry is not broken spontaneously. Which means that Q, let's call it Q star, the matrix that realizes this maximum is symmetric. What does it mean that Q is symmetric? Can you guess what is the form of Q? So you know that I should have 1 on the diagonal because this is imposed by the normalization of the x. So can you guess the rest? Huh? Zeros is a bit restrictive. 1 number, okay? So I will have just 1 number that I will call it Q, if you don't mind. So, sorry. Sigma. No, sigma is the parameter of the model. So, for the moment, what I mean is that if the matrix is replica symmetric, it means that Q12 is the scalar product of x1 and x2, for example, must be equal to Q23 because I can just call replica 1, I call it 3, and it must not change, okay? So all the elements of Q must be equal, okay, except the one on the diagonal. So if you want another way of saying is that QAB can only depend on whether A and B are equal or different. So if they are equal, I get 1, and if they are different, I get Q. Fine? It's the only symmetric matrix that you can have. So now the problem is very easy, because now I have only 1 number. So I can put this into the function A of Q, and I can see what happens. So when you have a matrix like this, okay, you can also, let me just, for future reference, let me write this as, I can write this as 1 minus Q times the identity matrix plus Q times, okay, how do you want to call it? I. Oh, I was the other function, J. So J is the matrix with all ones. Okay. So in general, a replica symmetric matrix is always a linear combination of the identity plus the matrix with all ones. Now, OK, I will come back to this, but what is good is that this is the matrices that have this form, they form a closed algebra. So if you multiply two matrices of this form, you still have a matrix of this form. And if you take a linear combination, of course, this is also true. And the other, OK, and once you have this, it's very easy to diagonalize this matrix in general. So you can compute the eigenvectors and eigenvalues. And from that, you can get the determinant. So the determinant of this matrix is just going to be 1 minus q to the power n minus 1 times 1 plus n minus 1q. OK? OK. So now, in A of q, now the function A of q, once I put in this form, will become, I will call it little a rs of q, which now depends only, I mean, before it was a function of a matrix, now it's a function only of a number, which I call little q. And how does it look like? So the first term is 1/2 log that q, so it will become 1/2 times n minus 1 log 1 minus q plus 1/2 log 1 plus n minus 1 q. And then I have plus alpha times the other term. OK, for the moment, I leave it like this. So, OK, now this still depends on n. Now what I have to do is that I have to, in principle, I should first maximize with respect to q for each n, and then send n to 0. But now you see that now this is explicitly a function of n. So what I will do to simplify the calculation is that I will first send n to 0 and then take the maximum over q. OK? You have to think a little bit to be sure that this is correct, but OK. I don't have time to enter into so many details. So what I do now is I want to take, to get the free energy, I want to take the derivative with respect to n and send n to 0. So what you see here, if I take the derivative with respect to n, I will just select the linear term. So I will get 1/2 log of 1 minus q. And here I will get plus 1/2 q over 1 minus q, which is the linear term that I get from this one. Let's hope so. Yes. The only thing that does not commute, if you want, is that the minimum, I mean the maximum over q will actually become a minimum when n becomes smaller than 1. And this you can check if you put alpha equal to 0. So if you don't have constraints, just have a sphere. What you expect is that the solution will be q equal to 0. Because if you don't have any constraint, the replicas can go everywhere, and typically they will be orthogonal. Okay, so you can check that q equal to 0 is always a stationary point. But when n becomes, if you take this, so if you drop the term with alpha, just take the entropic term, you can check that this one has a maximum in 0 for n bigger than 1. But when n becomes smaller than 1, actually it becomes a minimum, because you have a global n minus 1 in front that will change the sign. So this is a problem of the analytical continuation, that you have to exchange a maximum with in a minimum. OK, then the other thing is that, OK, so we computed the entropic part of this thing. And I will not have time to do the calculation of this, but you can do it. So if you take this structure for the matrix q, you put it into the expression of the function I of q that I gave you before, you work a little bit. This is really tedious, so I will not do it. And you get to this form. So you have an integral over h of e to the minus h squared over 2q divided by square root of 2 pi q. So this is the Gaussian integral times the log of the integral over z of e to the minus z square over 1 minus q divided by square root of 2 pi, so another Gaussian integration. And here you have exponential of minus beta v, where v was always the potential of h minus sigma minus z. So basically what you have to do, you take your potential, first you do a convolution with the Gaussian of variance 1 minus q, then you take a log, and then you take another convolution with another Gaussian with variance q. And this is very similar to what Florent did, but he had additional integrals because he was doing the teacher-student, I mean the planted calculation, where the disorder is generated by a planted configuration, so you have to do some additional integration. Here you just have this. It's maybe time that I switch to the other. Okay. So this concludes. So this one now is the replica symmetric form that now is a function of only one number q. You have to find the stationary point, which will be a minimum. And once you do that, then the free energy of your problem per spin is going to be minus t times a of q star, where q star is the minimum. The minus t comes because you see that this is log z. So in order to get the free energy, you have to multiply by minus t. So this is why you have this minus t. So under the assumption of replica symmetry, you only have to take this function that requires 2 integration to be computed, find the minimum with respect to q, and you're done. So this concludes part 2b. Okay. And now we can discuss the SAT and SAT transition. Where can I do it? Is it fine up to here? Yes. This one? Okay, it's a matter of notation. So I call big A the function of the matrix in general, and I call little a the function when I assume that the matrix is replica symmetric. If you want, this is little a. This still depends on n, and then I'm taking the limit n to 0 and the derivative with respect to n, and I get this. Insist if you're not convinced. What's
So if you take n goes to 0, you get half. You differentiate first.
Yes. So what I'm exchanging the operations. So in principle, I should first find the maximum over the matrix Q for integer n. Analytically continue to real n, take the derivative, and I get the free energy. I'm exchanging the operation. So what I'm going to do is I assume that the matrix has that form. Okay. I plug this form into the function big A, and I get this function that now depends on n. And then I take n to 0, and I take if you want, I take the linear term in n in this thing. So I derive with respect to n, and I send n to 0. And this gives me this thing here. I mean, if you're not convinced, you can also write it for general n. And you can, for each n, you can compute q. Q will be a function of n, and you can check that when you send n to 0, you get the right. So this is really not dangerous, this exchange of. Okay? Okay. So we have this thing. Now, remember that Q is the scalar product between two different replicas. Okay. So now I want to take the limit of temperature going to 0. And I want to study the SAT phase. What do you expect for Q in the SAT phase? When T goes to 0, how should Q behave? What should happen to Q? I mean, of course, Q is smaller or equal than 1 for the triangular inequality. And you can see that when Q goes to 1, this is probably also an answer to the question that was asked before. When Q goes to 1, this object becomes singular. So this is done in such a way that Q will stay between -1 and 1. I mean, actually between 0 and 1. So what do you expect when temperature goes to 0 in the SAT phase? What should happen to Q? I mean, there are two possibilities, so you have to choose one. If you want. One possibility is that Q goes to 1, and the other is that Q goes to some Q0 smaller than 1. Which one of the two? Okay, nobody wants to take the risk. So the point is that in the SAT phase, what happens is that you have your sphere. So you have a constraint. So this will be phi 1, first constraint. This is going to exclude some part of the space. Now I put another constraint, phi 2. And this is going to exclude another part of the space. But so if I am in the SAT phase, there are solutions. So what I expect is that I have some volume, which would be now this one in this example. There is some volume where I have solutions. If the volume is not 0, then when I integrate, I have a finite volume. And when I replicate the system, now I have two replicas, x1, x2. And there is no reason why they should coincide, right? They will fluctuate. Each replica will fluctuate a little bit into this volume, right? So in general, the overlap will be smaller than 1, because they're fluctuating a little bit. It's like, I don't know. OK, it's like nothing. I mean, OK. So this is really an important point. So if it's not clear, ask me. Even later, ask me. It's important. So what I'm going to do to study the SAT phase, I'm going to take the limit of 0 temperature with Q smaller than 1. So if I do this, if Q is smaller than 1, you see here I have my expression for A. I have to find the minimum of this thing. OK, this part is, if Q is smaller than 1, this part is fine. Nothing happens. And here I have a convolution with respect to Q, another convolution with respect to 1 minus Q, and I have this function. You see that the only way, I mean, if Q is finite and beta goes to infinity, the only thing that will happen is that exponential of minus beta v. Now, you remember that v is positive for negative h, and v is 0 for positive h. So this is just going to become theta of h, right? Because when h is positive, v is 0, and this is 1. When h is negative, this is positive. So exponential of minus beta times something positive will go to 0. It looks like everybody is lost. Yes?
So when the dimension of this sphere goes to infinity, doesn't it mean Q should also go down to 0?
No. If Q goes to 0, means that the replicas are typically orthogonal. So this means that basically they can sample all the sphere. So it could be that in the end Q is 0. For the moment, I'm just asking is it going to 1 or not. I mean, let's say if Q goes to 1, it means that all the replicas coincide, right? So it means that there is only one solution. I'm claiming that this is not the case in the SAT phase. It could be that in the end Q is 0, which would mean that the constraints are weak enough that basically the replicas can move everywhere. This happens in some models. Here Q will be non-zero, but not 1. Okay. Okay. So under this, so when I take this limit, I get this is going to be 1/2 log 1 minus Q plus 1/2 Q over 1 minus Q, and then I just have to. This will be alpha integral over dH. I will call a Gaussian of variance Q. I will call it gamma Q. And then I get the logarithm. And now this is the convolution of a Gaussian with a step function, with a Heaviside function. So it's an error function. And I will call it, so this will give me what I call theta of h minus sigma divided by square root of 2, 1 minus q, where theta is 1/2 of 1 plus the error function of x. So it's basically, it's a smoothed Heaviside function, is something like that. Okay, so this is the convolution of a Heaviside function with a Gaussian. Okay, so, and then I have to find the maximum of this thing. The minimum, sorry, over Q. Is it fine? If it's not fine, please ask. If you're never, if you're not even in the position of asking questions, it means that really you're totally lost, and that's bad. Okay, let's try to go. I will continue, but please ask, or otherwise next time you can. So just to recapitulate. So I have this thing that is in general the replica symmetric expression that I have to minimize with respect to Q, and this depends on temperature and on alpha and on sigma. So the control parameters are alpha, sigma, and the temperature. So what I want to do is I want to send the temperature to 0, but there are two possibilities, as I will show. In the SAT phase, what I expect is that I have a finite volume. The replicas move a little bit, so Q is smaller than 1. And so I get this. Now, what happens when I approach the SAT-unsat transition from the SAT phase? What's going to happen is that I add more constraints. So I fill this space until at some point the volume of the solutions goes to 0. So there are not, at this point, there are no solutions anymore. And then it means that, the replicas, they will all be constrained to be in the same point, which is the only solution that is that remains before disappearing. So Q should go to 1, okay? So Q should go to 1 when alpha approaches the SAT-unsat transition from the SAT phase. And by the way, so this is the function A of Q in the SAT phase. It doesn't depend anymore on temperature because I sent the temperature to 0. And the only thing I have to do is to minimize with respect to Q. Once I do that, I get the free energy. The free energy is minus T times this function. That does not depend on temperature anymore. So this means, if you want, that the free energy is going to be linear in T. What does it mean if the free energy is linear in T? Remember that in general the free energy is E minus Ts. So if the free energy is linear in T, this means that the energy is 0 and the entropy is constant, okay, something. Okay? So the minimum over Q of this function is going to be the entropy of your system, and the energy is 0, which is correct because you are in the SAT phase. So the energy should be 0, and the entropy should be finite. Okay? So this function is exactly the entropy in the SAT phase. I mean, after you minimize over Q. So what happens when Q goes to 1 from the SAT phase? You see that here I have a log of 1 minus Q. Here you have this 1 minus Q. So this thing is going to diverge, which is correct, because when I approach the SAT and SAT transition from the SAT phase, the entropy should go to minus infinity, because the volume is going to 0, and the logarithm of 0 is minus infinity. Okay? So this is the good limit. And now let's just finish on this. What I can do, when Q goes to, and now I'm looking to at which point the minimum of this thing over Q is going to go to 1. And what you can do, so I can take the equation for Q. Okay, the equation, do I have a sticker blackboard? So the equation for Q is that the derivative of A with respect to Q should be 0. And this gives me 1/2 Q times 1 minus Q squared, which is the derivative of this first part, plus alpha times the derivative with respect to Q of the integral over H of gamma Q times the logarithm of this theta. And what you can see, so this should be 0. When Q goes to 1, this function, the logarithm of theta, you see, if H is bigger than sigma, then and Q goes to 1, then this becomes plus infinity, and this goes to 1. So the logarithm of 1 goes to 0. So if you want the logarithm of theta of H minus sigma over square root of 2 minus Q is going to be 0 for H bigger than sigma. And on the other side, theta is going to 0. So how does it go to 0? Theta, you have to look to the asymptotic properties of the error function, which is basically Gaussian when the argument. So this is going to be minus H minus sigma square over 2 times 1 minus Q for H smaller than sigma. Okay? I'm sorry, maybe you can't read from that side. But anyway, it's just Gaussian. So if you plug this asymptotic here, what you get is that the equation for Q becomes 1/2. So Q is going to 1. So this Q, I replace it by 1. So you get 1/2 times 1 over 1 minus Q squared plus alpha. And here you replace this by the asymptotic. So the asymptotic will be, so this will become an integral between minus infinity and sigma, because for H bigger than sigma, this is 0. Here I get H minus sigma squared divided by 2, 1 minus Q, with a minus. So when I take the derivative, I get alpha, integral between minus infinity and sigma of gamma. This Q will be 1 times H minus sigma squared. And here I get 2, 1 minus Q squared. This should be 0. So Q, this term goes away, this term goes away, the 2 goes away. And I get 1 equal to alpha times this integral. So I get alpha equal to 1 divided by the integral between minus infinity and sigma of dh of gamma 1 of H times H minus sigma square, which is the SAT and SAT transition point as a function of sigma. Okay, so we arrived to the result. So we are here, okay? So what we did, and then I conclude. So we obtained the general expression of the replica symmetric free energy, which is this. And then I said, okay, now I want to take the zero temperature limit. I take the zero temperature limit in the SAT phase, where Q is smaller than 1. I get something, and then I say, okay, now in order to find the transition point where the SAT phase does not exist anymore, I have to send Q to 1. And Q goes to 1 when alpha reaches this value here. Which, by the way, for sigma equal to 0 is equal to 2. And, OK. Yes?
So at some point, when you convolve the Gaussian with the Heaviside function, does that mean that you picked a potential?
No, for the moment, the potential, for the moment, I don't care. I mean, the only thing I used about the potential is that it is positive when H is negative.
Okay.
But I didn't, it's not important, because in the end, whatever potential I use, it will always go to infinity when beta goes to infinity. So it will become a hard sphere potential, basically. It will cut completely the negative part. So if any constraint is violated, it's minus, and the energy is infinity.
Okay, so it doesn't matter what you pick for that curve, right?
It doesn't matter. For the SAT phase,
Right.
we will see tomorrow that in the unsat phase, then it will matter, because I will visit the negative, I will violate the constraints, typically. So then what I use for V, then it's important. But in the SAT phase, no. So this result is independent of the potential I use. And if you want, I mean, you could even from the very beginning choose a potential that is infinity when H is negative, so the energy is infinite. So you completely forbid any violation of the constraints, and you get to the same result. So that's a very important point, because it will come back in the discussion with the. OK, so I will. Yes. Sorry, gamma Q is a Gaussian with variance Q and 0 mean. Sorry, it's a notation that I said it too fast. So, OK, so I think, at least I hope I met this goal. This one should be done. I mean, we computed the SAT and SAT transition line of the perceptron. By the way, if you plot it, it will look something like this. Alpha sigma, it will look something like this. So for sigma equal to 0, alpha is equal to 2. Here it's SAT, and here it's unsat. And this is the result of Derrida and Garner 1988, this paper. So I think this is done, and we did a simple replica calculation in the sense that it's replica symmetric, and we will discuss this tomorrow, but this is correct. I mean, in this case, the replica solution, the replica symmetric solution is correct. Okay, you don't have to break, and I will explain you why. So this remains to be done for the next lectures, and I think that's it.